Hi everyone, this talk is called This Dump is a Puzzle, Reconstructing J2 Micro Edition firmware from an unknown file system. I'm going to talk a little bit about how I came to this problem, and I'm going to skip that slide because it's low content. But anyway, so I'm a security consultant at NCC Group. I've been with them since late 2015. I came into security from a previous hobbyist background, and I'm describing myself here as a heavily multi-class hacker, which means I dip my toes into quite a lot of areas. I previously have some education in maths, but I'm also interested in hardware, AppSec. I do amateur radio and obviously some reverse engineering. So once upon a time, I was investigating an IoT gateway device. It had a chipset that was running on J2 Micro Edition midlets, which themselves run on a proprietary JVM and real-time operating system of some sort. The device itself bridged from low-power wireless access network over a GSM link to a private APN, a private network, and that was a kind of security feature, presumably against sort of interception of messages from the smart network over to the back-end services that integrate with it. I had taken the usual sort of device local exploitation routes of finding an unsecured debug port. None of that's particularly interesting, and what I really wanted to do is see if I could find a way into the back-end services themselves using the resources available on the board. So we have an embedded SIM card on the board. We want direct APN access to the back-end systems because they're way more interesting than a little smart home network. So I desoldered the SIM, and I apologize for this. I did this really, really disgusting kludge onto opened up mobile GSM modem, and mysteriously it all worked despite this disgusting loopy wire thing. However, in order to get there, we still need the APN config and the creds to connect to it. So I tried looking for those inside the environment itself. I tried looking for those extracting from the SIM card. So I say SIM card, it's a little IC. I tried using a logic analyzer to man in the middle the bus between the SIM and the main GSM module. I wrote a little parser. It was really super interesting, but nothing actually useful came out of it. And at that point, I gave up and decided to dump the GSM module chip itself and start digging through that and see if I could find anything useful there, because I was getting a bit desperate. And sure enough, inside the memory dump, I can see zip file fragments, and obviously that's Java midlets, the jar files, and that's the J2ME data where the configuration probably is, given I've eliminated all the other possibilities. Going through the chip dump going through the chip dump, I can't, for some reason, extract it. I start digging through it in a hex editor, and I can't find any file system magics or any other identifiers that particularly find a way to extract the file system. I found a whole bunch of regularly sized pages, but I can't find the page table, and I was struggling and not successful in reverse engineering the file system. And I'm just going to show a quick demo of that. Here we go. Let's see if I can get that on here. Right. So, yeah, so I'm currently listing the carve of the file system that I'd taken. It's about 10 megabytes. It's not that big, which you don't really need much for micro edition Java. There's finding a huge number of zip file headers, but when you start digging into the actual extracted data, what you shortly after find is that there's very little of it that's actually comprehensible, because the decompression is completely worthless because the pages have been placed in this file system out of order and we don't have the correct ordering. So as you can see, that's completely useless. So going back to the chip dump itself, this leads to the inspiration for the piece of research which I did, which was, given that zip files have a lot of internal structure and metadata and reference, like pointers within the file to other locations in the file, how can I use that? If I can find that data in the file in the dump, how can I use that data to make up for the fact that I don't have a page table whatsoever? And I'm essentially treating the dump as a series of pages which have then just been shuffled into an order. I don't care what order they've been shuffled into. How do I take the information that's available without any knowledge of the file system and try and make a massive shotgun parser to try and reconstruct the Java midlets? I'm just going to do a quick sidebar onto why it is that the decompression doesn't actually work, because many of you will be aware from carving files that you can typically unpack deflated zip streams that are in memory. The issue is that the packing of pretty much any compression algorithm is very, very dense. It's very non-redundant. And once you have a cut in the middle of the decompression stream, you lose so much context that you can't actually carry on from there just naively. You actually need to find a way of either reverse engineering the context back into a state where you can carry on the sort of state machine that the decompression algorithm is implementing, or you need some sort of other way to unpack it, because that data's gone until you've built it back up yourself. There's a sort of loosely related problem that happened with the Intel Management Engine reverse engineering project that Positive Technologies did and a few other people did, where there was the Intel Management Engine firmware was transported in a Huffman table, sorry, an LZMA, I think, format, but the Huffman tables were removed from it, and that was their obfuscation mechanism, preventing people from being able to extract it. And some people did find a way to reverse engineer the Huffman tables just from the zip data itself, but it's quite significantly hard work. It was beyond what I was able to invest in it. So in terms of how the zip file, because I'm trying to use the zip file data to reconstruct the zip files from their own juggled up selves, we need to start looking at what a zip file looks like. And one of the really helpful things in this was Ange Albertini's Kokami project. You probably all know him from the file format stunting in proof of concept, but he also does this amazing project with loads of posters of binary file formats, and they're really, really helpful with getting an intuitive feeling for how the files are structured. And I was reading a huge amount of his work at the time that I was sort of starting this project. It was really, really helpful. You can see that at the end of the zip file, where it says start, we've got the end of central directory record, and that's got a pointer into the, there's a pointer relative to the zip file itself for the central directory start, which is a big table of headers which themselves have pointers into the local file header data, which is then interspersed through from the beginning until the start of the central directory header in the zip file. So in terms of what our pages look like, we get pages, and I've kind of set them as separate blocks here, because as far as we're concerned, whatever order the pages are in the dump doesn't matter, because the page ordering is wrong. So we've got pages where we start halfway through a central directory and we end halfway through a central directory. It's central directory headers all the way through. We've got pages which start on a deflated data stream. We have bits of local file headers split in between the deflated data streams for the various files in the format. We have somewhere in the dump, we have an end of central directory for the zip file, and after that there's loads of Fs, which is pretty straightforward. That's just what happens when a piece of flash memory hasn't been written. And we've got other areas where we see either the start of the central directory block, or we get bits of deflated data which you identify by just very, very high entropy pages where there's no actual identifiable data within them. They're just sort of independent, and we don't really have any context about where those come in the whole dump. And that's that's just an overview of the sort of pages that we're trying to operate on and trying to interpret the data inside of them. In terms of characterizing the dump, if we're going to be reshuffling the pages into a correct ordering, what we need to do is skim through the dump in a hex editor, find the page size, the correct page size, and start working out what the lowest common denominator is for the page size, because that's the quantity, that's the basic minimum quantity that we want to be operating on in terms of reconstructing the file. If we go smaller than that, it's not very efficient. If we go larger than that, we'll reconstruct it wrong. So we start by finding the central directory, we find the end of central directory, and that looks like this. It's got a magic signature at the start of it, pk/x05/x06. It's the final record in the zip file, which means that only one of them occurs in any given zip file, which means we now have a way of counting the number of zip files that we're looking for in the dump, which is it turns out to be really important. We also have the size of the local file header segment and all of the associated data, because that's the offset of the start of the central directory is the same value. We also have the size of the central directory, and if you add those together, you get the location within the given zip file of the end of central directory, which we've just found by searching for this file magic. So I do a quick search for that file magic, and there are two of them, and this is a problem. The primary issue with this is because we've got all of these relative pointers inside of zip files, but those relative pointers are absolutely meaningless if we're mixing pointers from different zip files together, because they'll collide with each other, and all of the data that we're trying to reconstruct is completely incomprehensible. And there are, as you saw in the bin walk, there are actually quite a lot of these headers are identified by bin walk. There's roughly 2,000 of them, and that's a really problematic number to be trying to classify manually in any way. And also, I wanted to create some sort of, what I'm going for here is a general purpose solution that's essentially solving this problem for the general case. I don't want to just dig through and find some classification that I can then apply kind of to this specific problem. I want to solve the problem because I'm really interested in the problem and not really the dump. So I need to automate that, and in order to automate that, I need to find some classification data, and a really, really fantastic candidate for the classification data is the central directory headers. These have a magic value, so they're easy to identify. These have version data, which is specific to the operating system and the particular software stack that was creating the Java the Java medlets. They also have compression flags and compression method, which will typically be deflate for a zip file, but it's hypothetically possible it could be something else. And they also have a timestamp, which will be specific to the process. There's a slight problem with the timestamp as a classifier, because if you're using, for instance, the time, the same time in terms of hours, minutes, and seconds happens multiple times in a day. So that's, you can't really, you could end up with 12 o'clock June 6th, 2016, and 12 o'clock June 6th, 2018. And whilst those are very, very disparate times, you could have a very, very, very similar time code in this particular format. So I had to convert it all to Unix epochs so that you maximize any distance between them. So then I Googled and found a clustering algorithm to save my hide on this one, and I passed all of the available central directory headers. I converted them into vector values that could be applied into this, applied as the first parameter, like a big list of vector values that could be applied as the first parameter of the clustering algorithm. I applied the number of clusters that I already know from the end of central directory headers as my second parameter, and clicked go. And there's a short animation here of what the k-means clustering algorithm looks like. It places a couple of markers randomly inside the data set, and then moves them until they sit nicely on a cluster boundary, essentially. That's the quick explanation on that one. So now we've got our central directories listed into two different piles. And the next step, because that's not good enough to start reconstructing the central directory completely, a lot of them are broken, as you remember from before, across the page boundaries. We need to reorder them. And in order to reorder them, we abuse the fact that files are written from the start until the finish, which is fantastically convenient in this case, because it means all of the pointers in the file are written start to the finish. And we go for the central directory header with the lowest pointer, and we move the entire page that it's from, because what we're doing here is piggybacking the information of the page locations to the pages we know where that CD is. We move the entire page from the first CD we find for each zip file into a location in a skeleton file that we're creating. And we move it to a location that we know from the end of central directory for where the central directory block starts. And we carry on doing that iteratively until all of the pages for all of the central directory blocks are set into separate skeleton zip files. And we keep going right on to the end of central directory page, and for each zip file we end up with something a bit like this, where we've reconstructed the entire central directory, because they run continuously from the start of the central directory block to the end. And that also means we have, for free, gotten back the missing central directory headers. As all of the pages are now in order, we can read across the page boundaries, and it's all good. From there, we've got the central directory header local file offset pointers again. Those point somewhere in relative offsets within each of the zip files, and I'm only showing one zip file here, obviously, but you have one of these for every zip file in your dump. The pointers tell us that the counterpart local file header for each central directory header is at that pointer, which means that we can then take the fact that the local file headers are entirely constructed of data that you can find in the central directory headers. We make a fake central directory header, and we then just go searching for that in the dump, and we can then place that page in the target location, which we know from the local file offset for each of the zip files. And that fills in the pages like this, and that's pretty much as far as I got, because I was actually, at this point, recovering a fairly substantial chunk of the data from the sample I was looking at. And I felt pretty satisfied that, like in return on investment terms, that was going pretty well. So I'm gonna show my proof of concept here, and I've actually re-implemented the whole thing in Rust, but it's not working so great. I ended up creating a perf bug that makes it completely unreasonable to make everyone sit through it. But here's my original Python proof of concept for this, and anytime now. So what we're seeing here is the end of central directory headers have been found. It's clustering all the central directories. It's panicking a little bit about bits it can't find, but that's okay. We're just trying to make the best use we can. We've got 70% of that file. There was 78% of the other file recovered and dumped. And we've got these zip files that I've created from the dump that are just reordered. And I've accepted that there's zeros in the there's zeros in page size chunks of the file at certain locations where I couldn't find the corresponding chunk, but that's okay, because you can see that there's bad CRCs on some of it, but it's actually recovering a huge amount of the class files. It's much, much more data than you were finding in the original bin walk. And I kind of fluffed the typing here a little bit, and I didn't have time to re-record the demo, I apologize. But I'm now looking for the configuration files, which are buried in the dump somewhere. And here we go. And essentially this is kind of done now, but you'll see it in a minute where I've got the, there we go. I mean, there's a huge amount of files there. You can see gateway.conf there. And I'm going to cat the gateway.conf. And here we go, anytime now. There we go. And woo! OMG, WTF, BBQ. Okay, so, and that was like, there's a really substantial amount of the data has been recovered from that dump so far. You can't fully recover any data segment that's bigger than a page size, or bigger than 2 page sizes at all. That's a hard limit on this. You can sometimes, in worst cases, completely lose a file. You can, however, try and use CRC data, which is embedded in all the files. You can then do a brute force search in order to plug some of the smaller gaps. You end up with a really significant combinatorics problem trying to, essentially you'd have to, in order to plug the bigger gaps, you would end up taking a sort of exponential permutation on a selection from a really, 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 really big available selection. And that just ends up this massive maths problem, which then collides with effectively brute forcing a collision on CRC32, which is a super weak hash function. So that's not going to, I'd say hash function and not cryptographic hash function, obviously. So the other issues with this, I still have a huge number of implementation bugs. I found it quite difficult to create synthetic samples to test my code on because all of this relies on a great many assumptions being maintained. The assumptions aren't necessarily transparent to me developing the parser, and these kicked me in the ass repeatedly throughout trying to develop it. But there are a lot of ways that parsing corrupt data can go wrong, essentially. And that's pretty much it. So, any questions?
So you talked about the analogy of like having a bunch of puzzle pieces and then you're trying to fill them in. Given that you have these kind of, essentially what it seems like after you've started to fill in some puzzle pieces, you have known gaps between the puzzle pieces and potentially you may also know the sizes of what those gaps are. Is it possible to try to just like stick puzzle pieces in until they fit the right size of the gap between different chunks to like...
This is where the analogy falls down. The puzzle pieces that I'm trying to manipulate are all square. They are all the same size, and effectively I'm just using the picture data of the images of the puzzle pieces to try and figure out what matches up next to them, but I don't have any sort of size or shape associated with them like you would with the actual puzzle.
And that's because they're all the page sizes?
And that's because it's a shuffled list of pages, yeah.
Okay, cool. And then, so the errors potentially then, is that coming in because of, do you think the like difficulty in having the data that's more than 2 page tables, or is it because maybe the k-means clustering isn't exactly filling in data to the right clusters, or what?
In terms of difficulty filling in gaps, it's you have headers that are broken across the edges of different things, so searching for things that match up in order to like find matching images between essentially creating a virtual image of what we expect is going to happen from the central directory into having the image of the local file header. You end up with those local file headers themselves being broken across page boundaries, for instance. So you end up with real problems there. There are a lot of ways. I said there are a lot of ways to for trying to parse corrupt data going wrong.
Question from the other side. So actually, a few very quick questions. So one, are you going to release this?
Yeah. Sorry, I'm gonna be releasing this afterwards. I meant to get it out beforehand on the NCC GitHub, but I will get it out shortly afterwards.
Thanks. The 7816, are you going to release that as well?
Pardon? 7816 parser. It was a really, really ad hoc script.
That's okay.
Yeah, it's not really worth anyone's hassle.
And the third one was, I know you were going for the general solution, but in terms of your combinatorics problem, how many missing pieces were there really that, like, you know, you could let something run for a while and possibly have filled in your whole file?
So combinatorics, I believe it's a binomial expansion in order to do. I can't remember I did maths for a couple of years at university, and it's a bit rusty because it's a long time ago. But I believe it's a binomial expansion, taking a selection. So it's really constrained. Sorry, the problem itself as a sort of complexity issue is dependent on the data sets that you're accessing. So if you have a massive dump and you have tiny page size, then you're absolutely never going to solve that one. If you have a tiny, 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 tiny dump and a huge page size, you're sorted because it's all good. But if once you tweak those parameters so you get more than a few possible selections out of a massive set, you're having a real permutation problem because the number of permutations available is just enormous.
Test.
Sorry.
Very nice work.
Pardon?
Very nice work.
Thank you.
Yes. So I had a question. So you had some pages that you identified where they should be placed, and did you try to kind of see if there is any sequence of the indexes from the original place and the place you found? So like maybe there is some kind of relations that could be obvious once you see the mappings.
You mean like a string that runs on from one location to another or something?
No, like for example, page 1 ends up at position 13 or whatever, and page 2 ends up at position 5 or something like that. And maybe
right, like a mapping trying to reverse engineer the mapping relation between the. So I didn't actually analyze that too hard, and it's probably an interesting thing to investigate. From my point of view, what really excited me about the whole piece of research was essentially completely giving up on any sort of relation to the original file structure.
Did you look at any data that was not in zip files?
Any data that was not in zip files? The data that's not in zip files was relatively... So if you have like plain text config files and stuff like that within the dump, then that's borderline easy to go, okay, so this is a chunk of that text file and this is a chunk of that text file. It's not creating the same problem of it all being compressed and kind of nightmarish to unpack. What I should have mentioned, I didn't mention, you can use the binwalk deflate stream method is another thing that you can do to try and unpack an arbitrary deflate stream from memory. But immediately that I tried to apply that to my particular dump, what I then get is the binwalk extracts the corrupt data wrongly and eats up every single bit of memory in the hard disk and crashes, and I couldn't save my recording of that because it just crashes. And yeah, like once you've lost the context for zip file data, then you need the context back. You either have to reverse engineer the context or you don't have it. So you can't just match up streams together, and that was why it was an interesting problem because it's such a particular problem to have the fragmentation happening inside of deflate streams.
No more questions? Then thank her again for her nice talk.
Thank you.